Hi everyone, I hope you're all well. We're going to try something a little bit different. We're going to try and go through the magnetism and electromagnetism topic using a range of videos. These videos linked with the PowerPoints, some other videos that I've made, and the booklet. So hopefully this will give you a little bit of an easier way to sort of understand some of that information. So let's get going. So the first lesson, the first lecture that we're going to be going through is going to be talking about magnetism, some of those common words that you might remember from some of the Key Stage 3 studies. We're going to try and understand how magnets work and what a magnetic field actually looks like. So the pages that we're aiming to go through today are these 3 pages, and what I recommend is that as you're following along with this video, you pause it, anything that you want to write down, you can fill in those boxes. It's quite explanatory where the bits from the PowerPoint go, but hopefully this will make it a little bit easier. We're going to start off obviously with the first page and looking at the poles of a magnet and the magnetic fields. Now, what do you know about magnets? It's quite hard to get your feedback, but one of the things you might know about magnets is that actually not all metals are magnetic, which is what a lot of people think. In fact, only a few elements can be magnetized, and those elements are iron, cobalt, and nickel. So they're the 3 elements that you need to know. Now, also we know that magnets have poles, north poles and south poles, and the poles of a magnet, these are the places where the magnetic fields are strongest. Now, I'm sure you all know what happens when 2 magnets are brought close to each other. If we get 2 poles like this, 2 south poles, they're both the same, so they're going to repel. If we've got 2 unlike poles, like here we've got a south and a north pole, then they're going to attract. And for completeness, if we get 2 north poles, then they're also going to repel. So remembering 2 like poles repel each other and 2 unlike poles attract each other. And this attraction and repulsion between 2 magnetic poles are examples of a non-contact force. They don't need to be touching for the forces to be exerted. Now later on we're going to have a look at the difference between 2 different types of magnets, permanent magnets and induced magnets, but for the moment we're just going to introduce permanent magnets. And these are magnets that are made of steel generally, and they don't lose their magnetism easily, which is why they're called permanent magnets, because they maintain that magnetism. Okay, so now we're going to have a quick look at the differences between permanent magnets and induced magnets, and you need to know the differences between them. It could be a really common 6-mark question comparing permanent and induced magnets. So the kind of clue in the first name, a permanent magnet produces its own magnetic field. It's always magnetic, whereas an induced magnet is a material that becomes a magnet when you put it inside a magnetic field. You can see an example of that in the other video that's linked to this. Permanent magnets can cause forces of attraction and repulsion, like we saw with our north and south, whereas an induced magnet is always a force of attraction. And finally, in a permanent magnet, again, like the name suggests, that magnetic field cannot be turned on and off. However, in an induced magnet, when it's removed from that magnetic field, it loses most or all of its magnetism pretty quickly and ceases to be magnetic anymore. So making sure you know the differences between the permanent and induced magnets. Now again, the other video, I show you how you can go about finding where the poles are of a magnet. So have a look at that video. But if you want those steps on how I did it, so the first thing I did is I put a compass near the magnet on a piece of paper. I mark the direction that the compass needle points, so marking a direction where the north is pointing. I then move the compass around to many different positions and I mark the direction that the needle is doing each time. And you can't do that and see that one there because I'm in the way, but it says you then join the points to show the direction of the magnetic field. So in class, when you're doing this, or if you're doing this, you'd have a chance to do it and you'd start to plot that magnetic field. And again, check out the other video to see how that works, but you'd get a diagram ended up that looks like this for our magnetic field. Okay, and what that's showing us is that the region around a magnet where a force acts on another magnet or on a magnetic material is called the magnetic field. When drawing it, it's really important you can draw this diagram, you can show what it means. Key things to point out is that the poles there, you can see the lines are close together. That's where the magnetic field is strongest. And the arrows are really important, the direction arrows. So how we work out those direction arrows is we think about what would happen as if the north pole was acting there. So at the north pole end, you can see that all the arrows are moving away because they're being repelled, because those 2 like poles repel. And at the south end, you can see all the arrows are coming in because it's being attracted, because the north and the south will be attracted. So always remember that the arrow lines go from the north to the south. And then you'll be spot on when drawing that diagram. Okay, we're moving very swiftly on. Remember to pause. I'm not expecting you to keep up as we go along. Use the fact that you can pause the video to stop, think about something, go away and research if you're not exactly sure what I'm talking about at that moment. We're finishing up with our third page and things to know. So like we said, the force between a magnet and a magnetic material is always a force of attraction. So they're always attracting magnetic materials to them. The strength of that magnetic field depends on the distance from the magnet. Okay, so the stronger you are, the closer you are, the stronger that field is. And as we said before, the field is strongest at the poles of the magnet. Okay, so the force of attraction, the direction of the magnetic field at any point is given by the direction of the force that would act on another north pole placed at that point. Sounds a little bit confusing at first, but let's just imagine if we put a north pole here over at the north, then they're going to repel. If they repel, then the magnetic field is going to be pushing away. It's going to have an arrow going away from it. If we took the other end at the south, we put a north pole there, it's going to attract towards the south, so it's going to go in. So if you think about that with the diagram that we drew earlier, always at the north it goes away, and at the south it's attracted in. And then finally, when we talk about compasses, there's a small link to compasses. A magnetic compass contains a small bar magnet, and the Earth itself has a magnetic field. And so a compass needle, why it always moves around, is because it's pointing in the direction of the Earth's magnetic field. So it's always trying to align itself with the Earth's magnetic field, which will therefore always point you towards the magnetic north pole.